The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The webinar will begin shortly. Please remain on the line. The broadcast is now starting. All attendees are in listen-only mode.
24. Biomanufacturing and Biofoundry Initiative is a new component under the BioRight scheme with a budgetary outlay of Rs 1,500 crores for 3 years, starting from 23-24 to 25-26. Through extensive national consultations and sectoral expert meetings, 6 thematic sectors have been identified for implementation under the Biomanufacturing Initiative. These include bio-based chemicals, APIs, biopolymers, and enzymes, smart proteins and functional foods, precision biotherapeutics, climate-resilient agriculture, carbon capture and its utilization, and futuristic marine and space research. A strategic roadmap has been formulated to implement these verticals under the Biomanufacturing Initiative. I'm happy to share with you today that the department has announced 3 calls for proposals. First on cell and gene therapy, second on smart proteins, and third on carbon capture and utilization for fostering high-performance biomanufacturing under the Bio-E3 policy. The call for proposals for other thematic verticals and the sub-verticals are being finalized and will be announced soon. Regulatory conclaves are also being organized to develop a framework for coordinated regulatory reforms for each of the thematic sectors, subsectors. The first DBT BARAC Joint Regulatory Conclave was organized on smart protein sector. At the heart of this initiative are DBT BARAC Polanco Bioenablers, a network of cutting-edge bio-artificial intelligence hubs, biofoundries, and biomanufacturing hubs. These cross-cutting technology platforms will act as a backbone for innovation, empowering all the 6 thematic sectors and accelerating India's progress towards becoming a global biomanufacturing leader. Towards this, the first DBT BARAC joint call for proposal titled Molankur Bioenabler, Biofoundries and Biomanufacturing Hubs was issued, and a large number of proposals have been received from across the country. The proposals have been evaluated by a multi-step competitive review mechanism, and the recommended proposals are under process for financial support by DBT. DBT will be out with a second call for proposals on bioenablers soon. Further, India's first biomanufacturing institute, the National Agri-Food and Biomanufacturing Institute in Mohali, was inaugurated and has been dedicated to the nation in October last year. I'm also proud to announce that an MOU has been signed between DBT and ISRO for cooperation in space biotechnology and biomanufacturing, and a joint working group has been constituted to identify proposals for joint submission. A center-state partnership conclave on the Bio-E3 policy, chaired by the Honorable Minister of State, Independent Charge, Ministry of Science and Technology, Dr. Jitendra Singh Ji, took place on 7th February 2025 at Gyan Bhavan in New Delhi. Discussions were held to facilitate collaboration between the center and the state governments under the Bio-E3 policy, where representatives from 24 states, union territories, science and technology departments, councils, industry stalwarts, as well as officials from DBT and BIRAC participated. During the conclave, the state governments were urged to set up Bio-E3 cell, which would serve as interconnected knowledge hubs linking state and national stakeholders. These cells are intended to ensure that biomanufacturing initiatives align with local priorities and resources while remaining connected to the national objectives. Outreach activities for the Bio-E3 policy are being carried out extensively to press meets, social media platforms, editorial and school campaigns to highlight its significance. To broadcast the activities under the Biofoundry and the Biomanufacturing initiative, our website has been launched. To further disseminate information about the Bio-E3 policy and discuss thematic verticals, DBT and BIRAC have launched a webinar series on Biofoundry and Biomanufacturing initiative. This series, Biomanufacturing of Biopolymers. Biopolymers synthesized from bio-based feedstocks can be used as sustainable alternative to petrochemical-based and non-biodegradable single-use plastics. Global market size for the biopolymer industry is US $9.93 billion, where the largest segment is non-biodegradable polymers, including bio-PE, bio-PET, bio-PA. The biodegradable sector that includes polylactic acid, PHA, starch blend, cellulose esters is also growing rapidly at a compound annual growth rate of 15.79%. Regarding the global production capacity of biodegradable biopolymers, starch blends account for 44%, PLA 24%, PHA 6% at industrial scale. Notably, India's bioplastic market is projected to grow at a CAGR of 24.36% to reach US dollar of 1420.870 million by 2027. There are potential gaps and challenges in these sectors, which currently hinder us in realizing the projected goals. These are insufficient availability of biopolymer monomers in the country. The current biopet production only includes 32% of the bio-derived monoethylene glycol MEG, while the remaining 68% is fossil carbon-derived TPA and is hence not biodegradable. PHA producing organisms have slow growth rate and face difficulty in genetic manipulation. Downstream processing costs and inconsistent PHA properties make it commercially non-viable. PLA requires very specific conditions to compose properly. Is an energy-intensive process and requires huge amount of carbon dioxide and releases huge amount of carbon dioxide to the atmosphere. Starch-based polymers used to make single-use polybags are moisture-sensitive, water vapor permeable, have low tensile strength, and high cost of blending. Uncertainties are present in the post-use processing and end-of-life options. There is a need to move from first-generation feedstock, that is sugar, to second and third-generation biomass-based feedstocks to make the process commercially viable. Having said that, there are several existing strengths and opportunities in the country in the field of biopolymers. Monomers like adipic acid, butanol, succinic acid, lactic acid, etc., can be produced through fermentation. Many labs and industries are already working in this direction. Industries are working towards making PET fully bio-based and biodegradable by replacing lithylic acid with FDCA monomer to make polyethylene furanate. PHA production is entirely fermentation based, and developing platform strains using synthetic biology will help in increasing PHA yields, and labs are already working towards this. We engineered PLA with modified mechanical properties to make it suitable for several applications, as well as for soil composting can be made through backbone engineering of the polymer by playing between racemic mixtures of L and D lactic acid, which can be produced through fermentation. PBAT and PBSA are flexible and suitable for making polybags. In addition to the starch-based blends, strength is an issue, but this can be tailored mixing PLA and PHA. PETase enzymes that degrade PET have shown rapid advancement in last 2 to 3 years. PET on degradation is converted to PDCA, which can further be used for the production of bioplastics. Policy push may enable the transition from conventional plastics to bioplastics in the single-use plastic segment. Today's webinar dwells on these issues in details. Once again, I warmly welcome you to the webinar on biomanufacturing of bioplastics and hope you find the discussions insightful and inspiring. Thank you very much.
Thank you, ma'am, for providing an excellent overview of the biopolymer subsector. Now, I would like to invite Dr. Ashwini Shetty, Praj Industries Limited, to present the industry perspective. Dr. Shetty has an extensive expertise in developing sustainable and innovative solutions for bio-based materials and green chemicals. She has been instrumental in advancing the use of biotechnology and process engineering to enable the transition to a low-carbon circular economy. At Praj Industries, Dr. Shetty plays a key role in translating cutting-edge research into scalable industrial applications, driving the development of technologies that contribute to sustainability and energy independence. Her work bridges the gap between research and commercialization, emphasizing practical and impactful solutions. Today, Dr. Shetty will provide the industry perspective on biomanufacturing of biopolymers. With this, I invite Dr. Shetty.
Good morning, everyone. Thank you, Dr. Amit, for kind words. Thanks, DBT, for this opportunity. Definitely, biopolymers is a very emerging area in India as well as globally. And Dr. Vaishali has given a nice overview of all the biopolymers that we can look at. I will be covering mainly the biopolymers which fall into the commodity sector, because there are many biopolymers which are also in the specialty sector like proteins and enzymes, and that I'm not going to touch today. We can go to the next slide. This slide shows probably a slightly different classification of biopolymers, mainly the commodity biopolymers. The first section is functionally advantaged biopolymers. So here, the molecule is completely different than the fossil-based plastic or fossil-based polymers, and it has different functionality and capable of replacing fossil-based polymers. Of course, bioplastic is a very, very prominent sector in all biopolymers here. So you can see PLA, PHA, PEIT, and there are other polymers like polyitaconic acid, polyethylene furanate. Uh, Definitely bioplastic dominates here. In case of drop-in, the chemically the polymer is exactly same uh, compared to the fossil-based polymer. Uh, just the route is it starts from bio-based feedstock, and then there is a third category that is directly extracted from plants. And here you can see starch and cellulose and protein based biopolymers and lipid based biopolymers. We can go to next slide. As Dr. Vaishali has mentioned, of course, there are challenges. And if you have to make biopolymers cost effective, we have to look at different aspects of the technology as well as the market. It starts from the feedstock, the strain development. If the biopolymer is fermentation based, of course, downstream processing or the pure separation and purification techniques are always high cost, and we have to pay very keen attention to developing these technologies. Tricky resin characteristic. This falls when, especially when we are looking at functionally advantaged biopolymers, because these needs to be these need to be uh, amenable to the existing infrastructure, and then only we can use these biopolymers in day-to-day life. And of course, limited economies of scale, and this is mainly because these this is an emerging area. Next slide, please. So for making it cost effective, as I said, that we have to pay attention to all the parameters which are listed on this slide, and we will go one by one into details of each parameter. Next slide, please. So when we call it biopolymers, it does necessarily mean that it starts from bio-based feedstock, and it can be either sugars or starches or cellulose or oils or gases. Of course, in India, sugar is abundantly available. In many of the cases of biopolymers, the stoichiometry is favorable to use sugars, and the amount of sugar or starches used for biopolymers is minuscule as compared to fuels, or it is getting diverted towards animal feed. Uh, Globally, if we see, less than 1% of uh, bio-based feedstock is getting diverted towards materials today. So there is a huge opportunity that we can use sugars and starches for making biopolymers. Uh, Oils, of course, edible oil is very, very costly in India. Non-edible oils, again, availability is an issue, but if we can use it, that's the best feedstock that we can use, especially for feedstock for biopolymers like PHA, where we can get good efficiencies also. Gases, of course, methane and CO2 have a potential, provided they are available at good cost, because uh, when we say whether it is methane or CO2, it's of course it's not free of cost. So we have to look at because methane today is used as a fuel, and then it has a very high price in the open market. So gas is not always equivalent to low cost feedstocks. So uh, from an industrial point of view, sugars and starches, of course, have high potential today in India as well as globally because of the cost effective nature. Next slide, please. If biopolymer is produced through fermentation, strain development is a key parameter that we have to look at. we have to pay attention to different parameters, like choosing the correct microbial platform, because the strain has to be really robust. uh, the cytometry has to be good with the strain. So you can't, or one can't get married to the uh, strain platform or the microbial platform initially and then go on selecting the target. It has to be always vice versa, that once we select the target and then go to the microbial platform, which is the most appropriate for production of that biopolymer. Genetic engineering directed evolution, of course, play very, very important role. Another important thing which is not really very glorified is adaptation and mutation, because these strains are really very robust. And when we start with bio-based feedstocks, it is not really necessary to develop the robust strains by genetic engineering every time for each and every inhibitor that is present in the bio-based feedstock. So adaptation and mutation play very, very important role. And we really, in India especially, in during when we learn strain development or we go through any literature, we really don't pay attention to this aspect, and this really, really needs good attention to pay to, because mutants really play a very, very important role. Apart from this, one needs to pay attention to whether we are going to pay attention to smart work or the brute force. So high throughput screening and everything is highly glorified. Is it really required is the question, because when we are looking at industrially robust strain, it has to be a combination of smart work as well as the brute force. So when we look at the strain development, there is there has to be
Please unmute, ma'am.
iteration from design, build, test, learn. So verification, then go to again to the design part. Next slide, please. Fermentation optimization plays again very crucial role in terms of media industrialization. First, high cell density fermentation in most of the cases is very, very important. Waste stream recycle is important from a making for making process cost effective. Fermenter design, very few people pay attention to, and for biopolymers like PLA, PHA, especially if you're using tricky feedstocks like oils and gases, fermenter design will play a very, very important role. And the next part is process scale up. So the results that you get at flask scale, not necessarily that we will get it at 100-liter scale, and not necessarily we will get the same results at probably 1 KL or 10 KL. So process scale up needs to pay attention to, and we have to optimize each and every parameter with respect to oxygen transfer, nutrient transfer, and maintenance of sterility throughout the process. Next slide, please. Product separation and purification is probably the costliest step when it comes to biopolymers. A very simple thing like solid liquid separation, like probably in lab we use a centrifuge, which is not economically feasible at higher scale. So one needs to pay keen attention to solid liquid separation. There are different options available like filtrations and many other things which can be used for solid liquid separation. Uh, uh, Green process is very important. One should not, or one should avoid to use solvents when we are looking at bio-based products. Enzymes are very efficient, and whenever possible, we can replace solvents with enzymes. Low temperature processes uh, needs to be there because high temperature again adds to cost. So if you pay attention to each and every parameter of this is going to have a substantial bearing on the cost of process. Minimal number of steps, this is a no-brainer. Energy and power integration across the process brings down the cost. Of course, achieving required purity and impurity profile is a deliverable of any separation and purification. Next slide, please. So while developing the previous slide, please. While developing the technology, application development really we don't pay attention to. When it comes to biopolymers, that is not the final product which goes actually into the market. Because whatever the final product we make from this biopolymer, like in case of bioplastic, either the bottle or the cutlery or the film that we are going to use finally, we need to pay attention to that. So Dr. Vaishali listed few of the problems that probably the end of life scenario or the cost. Many of these problems have been solved through application development. So cost effective, even if probably the neat resin may be slightly costlier, but if you can mix the cost effective polymer while developing the compound, that brings down the cost. That also can add the functionality like composting. Like in case it has happened with PLA, when it is mixed with pig bags, starch, and other salts, it accelerates its composting, and it is not necessary that one has to use industrial composting units for composting PLA. So this cycle starts with uh, first identify appropriate sector for your biopolymer, polymer characterization versus product requirement. Uh, Marrying these two plays very important role, especially when it is functionally advantaged biopolymer and the characteristic are not very well established. Like in case of new polymers like PEF and PHA, performance enhancement can be done through compounding, developing the new compounds, and working on product manufacturing. This can be done through research organizations if the product is completely new. In India, plastic processing industry or other industries are very well established. One can work with startups or even the established industries to develop new applications of these biopolymers, and of course the acceptance from end users. So one has to also work with the brand owners or the final users who are actually going to bring these final products into the market. So if you think of bioplastics, and if you think of films as the product, one has to work with either the food industry or the cosmetic industry who is going to bring this film into the final product into the market. And we have to pay attention to the requirements of either the food industry or the cosmetic industry from this film. Next slide, please. Scale of economies definitely play a pivotal role in bringing the costs down. Today, most of the biopolymers are costlier as compared to fossil-based replacements, and that's mainly because the scale of economies are uh, there is no scale of economy. The scale of production is pretty low. and there is always a inverse relation between cost of production and scale of production. Once the scale of production goes on increasing, the cost of production comes down. But market demand plays very important role, along with other cost contributing factors like feedstocks and application development and ecosystem development. Next slide, please. Having said that, if the technology is ready and it is economically viable, uh, other regulatory and government support plays important role. There has to be favorable regulatory structure and policy structure to support this new biopolymers. DPT is playing very important role in this case because of Bio E3 policy. DPT is supporting many industries to bring these biopolymers to in real world. In India as well as globally, there are regulatory structures which are panning out, and like in case of bioplastic, I can say there is INC, that is Intergovernmental Negotiating Committee, Global Treaty, which will form a blueprint for bioplastic across world. So different nations can use this blueprint to form their own regulatory structure. So I would say that or the different areas geographically across the world, what is happening, and we need to be open for the new ideas. Next slide, please. So as I said that India, next slide, please. India is at a sweet spot today because if we see 5 parameters that I've listed on the slide play very important role for commercialization of biopolymers. In India, we have abundantly available feedstock. Technology is available in India. There are many industries and startups are coming up with the technology. In terms of availability of expertise, we are at a very good state because we have skilled and competent workforce in STEM available across India. Of course, we have a demographic advantage, and people in the uh, working age, we have a lot of people there. Production ecosystem. So, if you see at access of power, water, and land at competitive price, which is available in India, transportation and logistic infrastructure developing extremely fast in India, and ease of doing business is improving in India. Apart from this, processing industry or the brand owners are warming up to the idea of usage of biopolymers in the industry as across the sectors. So next slide, please. So India can really become a vibrant ecosystem for cost-effective biopolymer production because of all these factors, and India is really placed at a sweet spot across the globe. I hope that I could give at least a glimpse of this sector uh, uh, for bioplastic as well as other biopolymers. Thank you.
Thank you, Dr. Shetty, for providing an comprehensive, excellent overview of the biopolymer subsector from the industrial perspective. Now, it is my pleasure to welcome Dr. Vinod Parmeshwaran, CSIR, National Institute for Interdisciplinary Science and Technology, Trivandrum, Kerala. Dr. Parmeshwaran is currently working as a principal scientist in the Microbial Processes and Technology Division of CSIR and IIST, Trivandrum, Kerala. His research interest includes sustainable bioprocesses, biomass to fuel and chemicals, biopolymers, and enzyme technologies. Dr. Parmeshwaran is a recipient of several awards and fellowships, including the Young Scientist Award from International Forum on Industrial Bioprocesses, France, Kerala State Young Scientist Award from Kerala State Council for Science, Technology, and Environment, Research Excellence Award from International Bioprocessing Association, France, Marie Curie, and many others. With this, I invite Dr. Parmeshwaran. Sir, the floor is yours.
Can you please unmute yourself, sir?
Yeah, thank you, Dr. Amit. Am I audible and my screen is visible?
Audible, sir.
Yes, sir.
Yes, yes.
Okay, my screen is visible, right?
Sir.
Yes, perfectly
Yes.
visible.
Thank you. First of all, I would like to thank Dr. Vaishali, Dr. Amit, and all the team of DBT and also the BIRAC for giving me this opportunity for a talk on the webinar series on Biofoundry and Biomanufacturing initiative started by the DBT under the BioE3 policy. So I also thank Dr. Ashwini for a nice talk, because you have covered almost all the part which I am going to present, so which made my work more easy. So I will be basically focusing on the biomanufacturing of biopolymers on academia perspective. So as you know that the term biopolymer is actually a really confusing word, because we are using a lot of words like biopolymers, bio-based polymers, bioplastics, and other things. So if you want to see the exact difference between these words, so the biopolymer is actually a broad class of material which is actually originated from biological resources, and that have the capability of degrade naturally. So all the polymers which have generated from the biological resources and also have the property of biodegradation is actually comes as the term biopolymer. And we are also using the word like bio-based polymers and bioplastics. So the bio-based polymer is actually a polymer that are derived wholly or partially from renewable biological resources. That includes plants, algae, or microorganisms instead of fossil fuel. So these bio-based polymers may be biodegradable or non-degradable. And bioplastics are a broader term that covering actually the plastics that are either bio-based or biodegradable or both, but that can be derived from renewable or fossil resources. So bioplastics can be either from the fossil resources or renewable resources. So here you can see that the biopolymers especially derived from the natural resources that includes plants, animals, or microorganisms, which includes cellulose, starch-based polymers, chitin, then protein, then polyhydroxyalkanate, which is a polymer that can be derived from microbial resources. Then bio-based polymers that can be partially or fully derived from the renewable resources, and that may be or may not be a biodegradable. And the examples include bio-based polyethylene, then polylactic acid. These are bio-based polymers, because in the case of polylactic acid, lactic acid is actually deriving from the microbial sources, and this lactic acid can be made into polylactate by chemical reactions, the catalytic reaction. And the bioplastics examples include there also the PLA, it's biodegradable, then bio-based PET, it's actually a non-biodegradable. Then PBAT. PBAT is also not a fully biodegradable. So these are the exact definition of different terms what we are using in the area of this biopolymer. So you can see that the biopolymers, as I mentioned, they can be non-biodegradable and bio-based, which include bio-based PE, bio-based PET, bio-based polytrimethylene terephthalate, etc. Then actual biopolymers, which are biodegradable and bio-based, including PLA, PHA, polybutylene succinate, starch blend. Then fossil-based, there are several polymers that can be made from fossil-based, but they are biodegradable, like PBAT, polybutylene succinate, then polycaprolactone. And here in this case, as I mentioned, this is actually derived from fossil based, but some of these polymers we can convert into bio-based. Like in the case of this PBT can be actually bio-PBT can also be derived, where adipic acid, terephthalic acid, and 1,3-butanediol can be used in the form for the synthesis of PBAT. So among these, the this adipic acid adipic acid and 1,3-butanediol can be produced through fermentation approach, and this terephthalic acid can be made through this biomass-based catalytic reaction. So with this, we can make some of these fossil-based biodegradable polymers into completely bio-based polymer. Similarly, like with the polycaprolactone, this can be made by the cyclohexane by oxidation. This cyclohexane can be produced through fermentation route. And there are actually this we need to compete these we can generally call it as a bio-based or biopolymers, but we need to compete this with this conventional polymer or conventional plastics which are fossil based and biodegradable. Here the thing is that it is not at all a sustainable way of using this polymer or production of this polymer, and this is not a biodegradable. So the thing is that if we mention some polymer as a bio-based, that does not mean that it is biodegradable. There are bio-based polymer, they are biodegradable as well as non-biodegradable. So if you see the classification of this biopolymer, we can classify based on the composition, which include polysaccharide-based biopolymers such as cellulose, starch, and chitin. Then we have a protein-based biopolymers, including collagen, gelatin, etc. Then polyhydroxyalkanate family of polymers, which include polyhydroxybutyrate, polyhydroxyvalerate, then polyhydroxyhexonate, and different kind of biopolymers that can produce through microbial fermentation. And also we have bio-based polyesters like PLA, then polyethylene furanate, then biopolyethyl PET, and then bio-PBS, bio-PBAT, etc. And based on the source of the production, we can classify these biopolymers into three, like microbial-based polymers, which include polyhydroxyalkanate, then xanthangum, then bacterial cellulose, PGA, etc. Then we have plant-based like cellulose, starch, pectin, and animal-based polymers like collagen, gelatin, keratin, etc. So, as in the earlier speaker already mentioned about the biomanufacturing of biopolymers, there are different operations involved in the biomanufacturing of biopolymers. The first thing is that the fermentation route of production of biopolymers, especially for the production of this PHA, then lactic acid, xanthangum, then polygamma glutamic acids. So there are several challenges we need to face on this bio-based production of fermentation-based production of these biopolymers. We need to see the optimum conditions for the fermentation, the optimum strain, and sometimes we may need to engineer the strain to get a maximum yield of these biopolymers. Then there are enzymatic polymerization approaches where we can use the bio-based polyesters like polylactic acid, where we can use enzymatic esterification or enzymatic polymerization. So for that, we need to develop the enzymes, suitable enzymes that can use for the polymerization of lactic acid into PLA. Then there are certain chemical modification of natural polymers, like we can use cellulose acetate and starch blends for modification of the polymer so that the property of the polymers can be improved. Then we need to have a efficient extraction and purification of process from the fermentation as well as from the biological step that already it is covered. And then that we also need to go for the downstream processing, like the recovery of the polymers, drying, and then modifications, and the final modification of the polymers in order to make it as a blend of the polymers so that we can get a more improved property of the polymer. Also, we need to see the final product applications. So all the biomanufacturing of biopolymers include all these operations, where starting from the raw material, and then the development of a fermentation approach or bioprocess approach. Then if need an enzymatic reactions or enzymatic polymerization, we need to develop an enzyme, then chemical modification of the polymers, then purification, extraction, purification, and downstream processing. As I mentioned, there are a lot of challenges in the biomanufacturing of biopolymers. Among this, the first one is the raw material and the feedstock challenges. So basically for the fermentation-based process for the production of polyhydroxyalkanate, we are basically using the high cost carbon source like glucose, glycerol, this kind of carbon source. So we need to look for the cost-effective and sustainable feedstock for the production. So agricultural waste could be one of the potential feedstock that can be looked into for the as a raw material for the production. Then when we use these agricultural resources like lignocellulosic biomass, there are also a lot of challenges, including the variability of the raw material and composition, variability in the composition of the raw material that also affect the microbial growth. Then the next challenge is on the microbial strain development and strain optimization. So normally the native kind of microorganisms normally have a low yield and productivity. So sometimes we need to go for a metabolic engineering or genetic approach to improve the strain. So that, that always sometimes affects the genetic instability of the engineered microorganisms on long-term fermentation. And also there are certain contamination risks that also affect the polymer production. Then comes the bioprocess engineering and scale up. So there are certain difficulty in the lab scale processing into scale up into an industrial level, because since we are looking in the microbial culture, sometimes in a small scale it may behave very efficiently, but when we look into a fermenter with maybe a 10,000 or 1 lakh liters of fermenters, so microbial strains may not behave as we expected. So these kind of scale up difficulties also we need to look into while developing the biopolymers. Then there is also a high energy demand and aeration requirement, which also add the cost of fermentation. And there are challenges in maintaining the optimal operation conditions like pH, temperature, and aeration. All those things also we need to consider in the bioprocess engineering and scale up development. Then comes the polymer recovery and the purification. Actually the cost of the major cost in the biopolymer development comes in the recovery part, the downstream processing, especially in the polymer recovery and purification, because there is a complexity in the downstream processing. So we need to see an eco-friendly and efficient extraction methods rather than using solvents. So we need to look for a green solvents for extraction of these polymers. And also we need to see the other cell debris and impurities that may also affect in the purification process. And also we need to see the economic and market barriers because as mentioned, most of these biopolymers are the production cost is very high compared to the petroleum-based plastics. And there is a lack of large-scale production infrastructure that is also actually hampering in this economic development, development of this process. And also we need to compete with the cheap non-biodegradable conventional plastics. So that is also one of the barrier which prevent in the market entry of these biopolymers. And also we also have a compliance with the environmental and safety regulations, and there is a need of biodegradability and the biocombustibility certification requirement. Also, we need to have a public awareness and acceptance of microbial derived biopolymers. So the major R&D limitations in the biopolymer development is actually the funding and investment gap. Is most of these R&D fundings come from the government grants like DBT, DST, CSIR, and BioRac, while the private industry investment is actually very low in this sector. So that is one of the limited funding, because as you compare with the Western countries, there are a lot of private industries, corporate industries are funding in R&D, so which is actually lacking in India. So we need to see how the more further funding can be involved in the private sector rather than we are looking for the government funding. and also the high cost of research in the biopolymer development, because the development of an infrastructure for fermentation reactors, then purification system, which make it difficult for startup and a smaller research lab to sustain for long term. And also most of our research funding are focused on short-term basis, because for the development of a sustainable biopolymer based on fermentation or other bio-based resources, there is as I mentioned, a lot of R&D in different sectors, like biomass, starting from the biomass feedstock, then fermentation development, then strain engineering, then downstream processing. So there are a lot of time and manpower involved in this process. So it is also a time-consuming affair. So rather than looking on short-term focus on research funding, we need to have a long-term process for scalability and commercialization. Then regarding the infrastructure and facility, most of the biopolymer research is confined to the academic labs with a limited facility, because in India, limited pilot plant test facilities available. So we need to look for developing numerous pilot scale facilities in different parts of the country. Also, or otherwise, we need to look into the other biorefineries, so that these biopolymers can be produced from the byproduct of the biorefinery. So that way also we need to look into the development of a pilot scale facilities in various parts. And we also need to look for the sophisticated equipment for developing this process out, because currently still we are basically focusing on outdated bioreactors and analytical tool. We need to look for the sophisticated system for testing and development of the process. And we have a large-scale biomass conversion and the process development. We have a limited access to the existing biorefineries. Some of these biorefineries are in the public limited companies, and the government-funded biorefineries are still, we have a limited access to that one. So that also we need to see the how we can access the biorefineries available in there that can be used for the production of biopolymers. And another limitation is the skilled workforce. India still lacks a sufficient number of the researchers who are specialized in the biopolymer development, especially in the synthetic biology, metabolic engineering, and the polymer science. And many academic research collaborations are still do not align with the industrial needs. So industry connections also we need to improve along with the academic R&D research. And even though we have a lot, the startup ecosystem in India is very good now, but regarding the biopolymer development, we don't have a very good startup ecosystem for a biopolymer as per se, because we are looking basically on the bioenergy and other biochemicals. So we should also look into the startup ecosystem where we can promote the startups to venture into the biopolymer, especially the fermentation-based biopolymer development. If you see the SWOT analysis of the biopolymer R&D, we have a very good strength on the abundant biomass availability, because India produces almost 600 million metric tons of agricultural residue that can be used as the raw material for the biomass production. And we have a good initiative like National Bioenergy Mission and Biotechnology, BIRAC and DBT. A lot of government supports and policies are available that actually our strength in this area. And we have a growing research ecosystems like IASC, IIT, CSIR, and ICAR have a very good ecosystem for R&D development on this area. And we have a very large pool of skilled scientists and engineers who have a relatively lower cost compared to the Western countries. So we have a very good effective workforce. So our major weakness is the limited industrial scale infrastructure, because most research at a lab or pilot scale, and only few large scale biomanufacturing plants are available. So that is one of the limitation. And another thing is the high cost of production of biopolymers because of the technological limitation. And we also have a slow technology commercialization process, because many innovations remains stuck in the research due to the lack of industry partnership and venture capital. So during the start of the research itself, the industrial involvement is really important, so as to make the process more faster. And also we have some regulatory hurdles because we have a lengthy approval process and lack of clear biomanufacturing policies. That also we need to strengthen. So regarding the opportunities, we have a growing demand of sustainable material because of there is within India as well as there is a global awareness about the plastic pollution. So there is a good opportunities for biopolymers development in India, and also the investment in circular economy as India pushes for a circular economy. So there we have a lot of opportunities in that circular economy area. Then the programs like Startup India, then production linked incentives for giving the loans to startup government-based loans, and those government incentive and funding are also very good opportunities, and we have a lot of export potential also. These bio-based these polymers, especially the countries like EU and the US, Japan, and other things. And we have a good synergies with agriculture and other industrial and other sectors collaboration, because we have a very good biopharmaceutical industry setup. So these kind of collaborations make it more, which can also help in driving the growth of in this biopolymer sector. The major threat actually comes from the petro-based material, because which is dominating the market due to the low cost and scale advantages, and the high-end biomanufacturing equipment and enzymes are often still depends on the import market. And also we need to see the market readiness and consumer acceptance, and there is a lack of clear policy on biopolymers, and we also need the economic and political factors include fluctuation in the policies and the international competition. That also we need to that is also actually a threat to in this sector. So the key trends that actually shaping the future of biopolymer R&D in India is we need to look on the focus on the agriculture and industrial waste as a feedstock for the biomanufacturing of biopolymers. We should focus more on the lignocellulosic biomass for the cost-effective production and cost-effective as well as sustainable production of biopolymers. And also we need to look on the effective utilization of waste streams that are actually generating from the existing agro processing industries and other industries. And also the future trend will be on the advancement in the synthetic biology and fermentation technology, as there is the improvement development in the CRISPR and metabolic engineering approaches, and efficient fermentation and bioprocessing, and now the precision fermentation and the artificial intelligence and machine learning driven the bioprocess and optimization process. That will also helps in the future development or future shaping the biopolymer development in India. And also we need to focus on the cost reduction as well as the scalability. We need to see the low cost and high yield bioprocess, and the investment in the pilot scale bio refineries to demonstrate the commercial viability, and also the eco-friendly extraction process also we need to look into, which is also very important in reducing the cost of production of biopolymer. And the another last thing is the circular economy and end-of-life solutions, because we need to have an innovative innovation in the compostable and marine biodegradable polymers. When at the end of life, if you throw the biopolymer in any ecosystem, marine or even land ecosystem, when it goes to the water, so the marine organisms can also able to degrade the biopolymer into its monomeric form. So that is also one of the important things we need to have look into in the future R&D. And also we need to have a closed loop recycling of these biopolymers, and also upscaling of this biopolymer, the waste from these biopolymers. That also we need to look into. And also we need to have a final life cycle assessment at the end of life studies. Also we need to see how these biopolymers helps in the further commercialization and the environmental benefit of this polymer. So the conclusion is that biomanufacturing of biopolymer is gaining a high momentum in India due to this environmental concern over the synthetic plastic. And presently the key focus is on the polyhydroxyalconate polylactic acid. And now lignin-based biopolymers are now many R&Ds are on the lignin-based biopolymers. And also people are focusing more on the renewable resources for the biopolymer, especially some bio-based polymers like bio-PBAT, bio-PVA, or even polyethylene furanate. These kind of biopolymers, newer class of bio-based polymers are actually starting on different R&Ds. Then high production costs, scalability issues, and low industrial adoption hinder the large-scale deployment. We need to see actually look on R&D on these aspects, and also have a partnership between academia and industry for facilitating the technology transfer, which also require further strengthening. And we need to develop a cost-effective solutions like research should focus more on the affordable feedstock and innovative processing technology, and the increased funding as government as well as the private funding, and also policy initiatives can also accelerate the progress. And we should focus on the circular economy, as India has a more potential in this area. We can become a leader in the sustainable biopolymer production if we focus more on the circular economy approach, where if we can develop a no waste, zero waste process biorefinery, that is actually one of the things we can more focus. And advances in biopolymer blend, because as we mentioned, in order to improve the quality of the biopolymer, we need to have a blending of different biopolymers. That also helps in the very good innovative biopolymers. So that way also we need to look into the advances in the biopolymer blend, and also the greener approach for the extraction and purification. And also we need to look for further advanced bio-based polymers. That will also help in the R&D development in India. So with this, I thanks once again DBT and BioRack for this opportunity. Thank you.
Thank you, sir. Thank you for providing an excellent overview of the subsector from an academic perspective. We will now open the floor for questions from our audience. Please type your questions in the chat box, and our team of moderators, Dr. Amit Kumar Tripathi from DBT, Dr. Sujit and Dr. Smita from BioRack, will assist in facilitating the discussions. Over to Dr. Amit Tripathi for the first question.
Yeah, thank you. So the first question is from Dr. Donald James to Dr. Ashwini Shetty. Dr. James is asking, what improvements are needed in logistics and storage to streamline the collection, transportation, and processing of renewable feedstocks?
Can you repeat it again?
Yeah, he's asking what improvements are needed in logistics and storage to streamline the collection, transportation, and processing of renewable feedstocks.
Okay, so all this logistics and storage will come into picture only if we are discussing about cellulosic feedstocks. With respect to sugar and starches, it is very well established value chain. So one need not have to pay much attention to, unless but the most important thing is availability. Of course, we need to pay attention to. With respect to cellulosic feedstock and oils, first thing is we need to pay attention to geography, in which geography it is available. The plant, there was no value chain available. By the time the plant is up and operational, this value chain has developed on its own. If we have to pay attention to, we have to pay attention that what are the important factors. Like in case of cellulosic feedstock, specific gravity is very, very important. So paying attention to making the bales and its transportation at cheaper cost. So one has to actually calculate that from the radius from which you are going to collect the feedstock. These are the few things that we have to pay attention to.
Okay, thank you, ma'am. The next question is from Dr. Apurva Sethi to Dr. Vinod. Dr. Vinod is asking, how should end-of-life disposal and recycling challenges be addressed to ensure that biopolymers deliver a net environmental benefit?
Yeah, actually, for the end of life analysis, we have different tools available, especially the life cycle assessment. So there are different software tools are available in LCA analysis. Even there are paid software as well as the open source softwares are available. You can go for Open LCA, which is an open source software, where we can actually analyze the end of life of a polymer, especially starting from the feedstock. Even if you are making a biopolymer from a agriculture feedstock, starting from the cultivation of agriculture, how much greenhouse gas is emitting while during the cultivation of the plant resources, and also extraction of the sugar from the biomass, as well as the fermentation approach, how this fermentation, whether any greenhouse gas or CO2 or other gases are emitting in the atmosphere. And also, when we make a biopolymer, what are the factors which involve in the biopolymer emission, whether it makes any ecotoxicity or environmental concern. And finally, when the biopolymer is in the market, how it emits any whether it emits any greenhouse gas or any other chemicals in the polymer. And finally, when we throw the material after our use, whether while degrading, how it emits the carbon, how it emit or how it degrade, or while emission, is there any other environmental hindrance or environmental factors are affecting in the emission. All these things can be studied in LC analysis. You can see a lot of literature, like there are one study on PLA, how PLA is degrading in the atmosphere. There are some studies showing that while the degradation of PLA, if you are not do a actual combusting of PLA emits more carbon dioxide than its production. So these kind of studies are available. So like that, we can study the end of life of a biopolymer. Even that can be, we can analyze LCA. There are different sorts of LCA, starting from cradle to grave, then cradle to grate. There are different approaches are there. Through this study, we can see the end of life of a biopolymer.
Thank you, Dr. Vinod. Just to continue, we have one more question for you from Dr. Rahul Shukla. That is, even with promising trends for applicability, biodegradable polymers opting from renewable sources present some disadvantages, such as low mechanical properties, rapid degradation rate, high hydrophilic capacity, and in some cases poor mechanical properties as well, especially in humid environments, rendering the application as unviable. So how to mitigate these challenges? So your thoughts on this, sir?
Yeah. So this is actually a very actually challenging thing what we are facing in the biopolymer R&D development, because most of the biopolymer, as you know, it is a biological origin. It is having an inherent property of absorbing water. It is more hydrophilic. So we need to see how it can make hydrophobic. So for this, we have other now people are working on adding different other biopolymers, especially the lignin. So lignin is more like a hydrophobic property. So whether we blend the lignin with the existing biopolymer, whether we can make it as a more hydrophobic. And also the lignin also imparts strength to the biopolymer. So like this, we can make different blends of biopolymers. So by blending with the different biopolymers, we can make it more having mechanical strength. Then we can make it more hydrophobic and also have a more application area.
Okay.
Thank you, sir.
Thank you, sir. The next question is for Dr. Shetty from Dr. Richa Kapoor. Variability is major challenge in biopolymer production. Due to this variability, what are the hurdles faced in the scale-up of biopolymer, and any likely solutions for these hurdles is what she's asking.
So I'm not very clear about Variability in terms of what? Variability can be in terms of the tighter yield, productivity, efficiency, and that can be controlled strictly mm, by following a very systematic process from lab up to scale up, doing repeatability and reproducibility tests, and getting it audited from the third party if you have any doubts. Of course, the third party audit always play a very important role. Even in research organizations, that can be done if you are transparent enough from a export from another lab or something like that. In terms of functionality is concerned, then if you remember the slide that I had shown, that detailed characterization of biopolymers play very, very important role in terms of the composition, the molecular weight, and other all other characteristics. If you test it at each and every step of production as well as separation and purification, then only you can bring the consistency in the final product.
Okay, thank you, ma'am.
So, one final question for Dr. Vinod. After that, we have one more question for Dr. Shete. So, sir, the question to you is from Dr. Harinder Singh. What frameworks can be adopted to perform comprehensive LCA of biopolymers to confirm their environmental benefits over traditional polymers?
So the major framework for LCA analysis should be I suggested the cradle to grave approach. So the complete LCA, starting from the raw material, then the process optimization, and the product formation, and also the recycling. Because the one major thing is that since even though the biopolymer is highly sustainable, so we should try to see once the end of life of that material is over, whether we can recycle it, and upscaling of the process, or even the closed loop recycling can be done to develop other kind of material. So this approach is one of the thing which we need to focus mainly, because if you see the life cycle analysis of these biopolymers, there are not very comprehensive studies on the complete or cradle to gate kind of analysis. So we need to focus more on the complete comprehensive life cycle analysis, and also the closed loop recycling as well as the upscaling processes, so as to have a better understanding of the polymer.
Thank you, sir. This final question is for Dr. Shete from Dr. Dilip Verma. He's asking, expensive purification processes, extracting and purifying biopolymers can be costly and inefficient, and solvent and energy intensive step. Some biopolymers require harsh solvents or high energy input for recovery. How to address these issues?
Very crucial and critical question, but there is no one solution for all the biopolymers. It is highly specific. It will change from the process to process, from the biopolymer to biopolymer. One thing, if you remember, I have also shown in my slide that if we can refrain from using solvents, that's always better, from making the process green, because that also adds to the final carbon footprint as well as the cost. Because when you're using solvent, you have to recover the solvents, and the cost of use of solvent is entirely dependent on the recovery of the solvent. If you lose more and more solvent, it is going to be highly costly. To make cost effective, look for the enzymes or other, mainly enzymes. Replacement for solvent is always enzymes. for solid liquid separation and other things, we have to look at the most efficient way. It may not have to be like centrifugation. We can look at the microfiltration, nanofiltration, those kind of filtration units. Number of steps plays very, very important role. Lesser the steps, better. When you are developing separation and purification, it is very, very important to work with the player who is going to supply your final equipment, because then only you get the idea of power required for that process, and the chances of recoveries. I think, but definitely there is no like thumb rule answer for which is applicable for all the biopolymers.
Yes, ma'am.
So thank you, ma'am and sir. So just to just address the participants who have been listening us in this platform and always also on YouTube. So due to time constraints, we will not take up any more further questions as of now. We request you to please send us your queries post the event where you will be getting a feedback form. So we'll be happy to answer your queries via mail. So that's all for now. Thank you. And also like to thank Dr. Aarti and Dr. Hemlata from BioLac who has joined us for this webinar. They're working in bio-based chemicals and enzymes verticals along with me and Dr. Smita for this webinar initiative. Thank you. Over to you, ma'am. And
thank you. Thank you, Dr. Amit Tripathi, Dr. Smita. As we come close to this insightful webinar, I would like to extend our heartfelt thanks to all our speakers for their valuable contributions. Your insights have shed light on the immense potential of this subsector of biomanufacturing of biopolymers. For those who were unable to attend live, the webinar recording will soon be available on the DBT website. Finally, please mark your calendars for our next webinar in this series, which will continue to explore various thematic areas of the Biofoundry and Biomanufacturing initiative. Details will be shared soon on the DBT and BIRAC websites and through various social media platforms. Thank you once again to our speakers, participants, and the organizing team for making this event a success. We look forward to your continued engagement in the upcoming sessions. Thank you.
Thank you.
Thank you, sir.